Welcome, everyone. This is the Empowering Women Summit 2020. We are starting our seminars right now. Today's topic is water desalination technologies and techno-economic analysis. Our guest is Sertac Akar, who is energy analyst at NREL. Welcome. Thanks for coming here today.
Thank you.
I can give the speech to you. And we
Thank
can
you, Carden. Right, thank you so much. So as Carden mentioned, today I will talk about the water desalination technologies and the techno-economic analysis of these technologies. Today's content is going to be a little bit loaded, but I will try to just mention briefly these content items. I would like to talk about the water desalination technologies briefly, and then I will continue with the current status of the water desalination, and I will try to give some summary of worldwide desalination costs, including the capital cost, the operations and maintenance cost, and the levelized cost of water. And finally, I will mention the National Alliance for Water Innovation platform, which NREL is involved, including the water desalination hub and the Techno-Economic analysis included in the Parity platform. So to start with, why water desalination is important. 75% of the Earth is covered by water. However, only 1% of the world water resources are fresh water. So water scarcity is increasing at an alarming rate, requiring a systematic approach to bridge the supply and demand gaps. Conventional demand and supply side management options can help elevate to scarcity, but pace of change is too slow. So luckily, there are technical and economic instruments to bring supply and demand into balance. And desalination can produce high quality potable water and suits the need of large cities. So to look at the sources of water, apart from the seawater, there are non-traditional sources which can be used for desalination, such as industrial, municipal reuse, conventional produced water, unconventional produced water, agricultural water, mining, power, and brackish water. So these are actually 9 main non-traditional sources that we take into account when we think about water desalination. And so water desalination technologies include some stages, such as a pre-treatment stage followed by a main treatment stage, and then maybe a higher recovery treatment stage, and finally a post-treatment stage helps us to desalinate the water. And we also need to consider the waste disposal, because all desalination technologies have high concentration waste at the end. So if you look at this flow chart in brief, so some of the main pre-treatment stages are coagulation and flocculation, lime softening, sand filters, microfiltration, ultrafiltration, and these are followed by the main treatment stages. And main treatment stages are basically electric or thermal. In electric methods, the most common one is the reverse osmosis and electrodialysis. And we also have some electrodeionization and ion exchange methods. There are some new technologies involved in the electric methods, which are forward osmosis, captive deionization, and electrodialysis metathesis. And the other important treatment technology is the thermal technology, which includes boiling water and generating steam and condensing the steam into desalinated water. The multi-effect distillation is one of the most common thermal methods, followed by the multi-stage flash. And there are also new technologies called membrane distillation, which uses a membrane similar to the RO technologies in thermal methods. These main treatment technologies are followed by high recovery treatment technologies, such as brine concentrators, crystallizers, or high recovery reverse osmosis systems. After these treatment stages, there is always a post-treatment stage to clean up the water, to make it more drinkable or potable by adding oxygens like aeration, by adding the ozonation, chlorine additions, ultraviolet cleaning, and sometimes even up to membrane bioreactor technologies. And after we clean the water, actually we clean the water, but we also create some waste. The condensate is highly concentrated water, which you don't want to just expose to the environment directly, and you need to have some waste disposal strategies. The most common ones are brine line, direct injection, using evaporation ponds, deep well injections, or even sometimes landfill. So this is the main summary of how water desalination looks like. If you look at the details of these technologies, as I mentioned, there are two main stages or three main technologies in the main treatment stage, such as multi-effect distillation or multi-stage flash technologies, which are under the category of thermal desalination, and reverse osmosis and electrodialysis under the category of electric desalination. So the thermal desalination basically uses the steam generation and condensing that steam into a condensed desalinated water throughout many stages, and then keeping the highly condensed water as waste and disposing to the disposal methods that we described earlier. But the electric technologies, which are more common, uses electricity for the main process instead of thermal, and then they use mostly membranes, such as the RO systems use those spiral shape membrane design, which allows the distillate passing through the membranes, and the condensate stays inside the flow channel and discharge out of the RO cartridge unit. Similarly, electrodialysis uses different membranes, but the main difference between the electrodialysis and the RO are using the anode and the cathode materials, which pulls the ions and the cations from the water system, which allows a purified desalinated water passing through the channel as a produced water. So after giving these brief introduction to these technologies, let's have a look at the typical layout of a desalination plant for seawater desalination. So this is an example from Tampa Bay, Florida, United States. And as you can see, this is starting with the intake from the ocean. And then this plant uses the cooling water of an existing power plant, which is the Big Bend power station, as the source water. And then it passes through certain stages of pretreatment, such as the sand filters and particle settlement, and this cleans up the water at the first pretreatment stage up to a level. Then comes the main treatment stage, starting with a cartridge filter and the reverse osmosis stages, and this gives us the product water. And this water is collected in a holding tank. This tank is in design 5 million gallons in capacity, and the wastewater is sent back to the brine line, which is discharged into the ocean back again. So this is a very typical example of a reverse osmosis seawater desalination. But reverse osmosis, even though being the most common, it's not the only one. Actually, we have other desalination technologies. If you look at the current status of water desalination in the world, as you can see from this graph, it's increasing since 1970s. And today's installed capacity is reaching up to 100 million meter cube per day as of 2017. So 63% of these installed plants are, as I mentioned, are reverse osmosis plants. But the thermal methods, such as the multi-stage flash and multi-effect distillation are also significantly high. And there are other hybrid and new technologies which corresponds to 3% right now under development, and which will increase their share in this pie chart in upcoming years. So, so of course, everything is a cost, and desalination is a cost as well. So if you look at the types of desalinations and geographic locations, such as the reverse osmosis in different locations, such as Mediterranean, the Arabian Gulf, Red Sea, the Atlantic, and the Pacific, you can see different cost numbers because the desalination cost changes by location and by technology. To just give a brief summary of this table, main capital cost ranges from $1 to $2 million per million liters per day capacity, and main operations and maintenance costs ranges between like 0.3 to 0.6 million dollars per meter. Sorry, dollars per meter cube, not million. And the levelized cost of water is also ranging between like 1 and 2 in this example, but we will see in next slides. It can be way more widespread in different technologies. So just after giving this brief introduction about how the desalination costs look like, let's take a look at the energy consumption required to desalinate the water. So as you can see here, we have two thermal desalination methods like the multi-stage flash and multi-effect distillation. We have some electrical cost between 2.3 to 4.5 kilowatt hours per meter cube, and additionally we have a higher thermal energy cost ranging between 5.6 and 8 kilowatt hour per meter cube. So in the RO systems at the last column, you don't see that thermal energy cost because everything is based on electric methods. So in most recent studies, especially at NREL, we are trying to integrate these renewable energy technologies into the desalination processes to remove these thermal costs from thermal desalination techniques or methodologies. And if we can remove this cost from the thermal energy, the total energy cost is almost in line or sometimes cheaper than the reverse osmosis technologies. So this is a very important area of research that we are working on these days. And these pie charts actually just shows the total cost in terms of the component, such as the capital cost is main driver in RO and also in the thermal desalination technologies. And as you can see, the electrical energy cost is less for the thermal systems, but it's higher for the reverse osmosis technologies. And there are also membrane costs, labor costs, chemicals that are consumed in the processes, and also some contingency or miscellaneous costs that you need to add to the total cost breakdown. So I think this brings me to the topic of the National Alliance for Water Innovation Platform and the Energy Water Desalination Hub, which NREL is involved. So I will give you a brief introduction to the NAWI, the National Alliance for Water Innovation. So this is a consortium including 3 national labs, 18 universities, and 12 industry partners, and many other contributors. And last year, the Department of Energy in the United States just announced, actually 2 years ago, they announced the funding opportunity for this energy water desalination technology. And then the consortium won this award for a $100 million funding up to a 5-year of project lifetime. And now this platform is trying to address the water security issues and the economic competitiveness across all economic sectors in the United States. and they are trying to focus on early stage R&D water treatment technologies and ways to treat non-traditional water sources. In this concept, NREL is involved in actually three main tasks, which are the water data and analysis management system, which includes collecting of all data available in the market across the United States, including the power plants, operators, university, research, and all industry partners, including manufacturing of these membranes and technologies. And then the second part that NREL is involved is the techno-economic analysis, which I am actually working on. This includes calculation of the levelized cost of water, the energy intensity, use of alternative energy and water resources, and in terms of their utilization, the water intensity in terms of meter cube per unit, and the system resiliency, which is also important, how the system is taken into operation. And the third part that NREL was involved is it includes the baselining, road mapping, and future scenarios, how the water technologies or how the water desalination will look like in the next couple of years, and how both the technology and the market will go. So this is the basic main three tasks that NREL is involved in this hub. And this is the part of the task that I'm involved actually doing the techno-economic analysis of this Parity platform. For this purpose, we just collect data from power plants, academia, published papers, and all available public sources, and collect that data in a platform to create a tool which can calculate that levelized cost of water and the energy intensity of those plants, using technically the total capital investments, the electricity costs, the catalysts and the chemicals that are consumed, waste disposal costs, the co-product values, such as if there are other value streams rather than water itself, such as you can exclude or extract lithium from water, which is an important source material for lithium-ion batteries, which is going to be very important in the future, or other kind of costs like replacement costs and fixed operating costs. This gives us the levelized cost of water in that certain power desalination plant and then certain location. So to give you more idea about how the platform works is we technically collect the data to fit into this framework, and we have the main treatment stages and the value streams, which we calculate the cost of gathering the water, treating the water, and also creating the value stream, such as distributing that water to the market, plus any additional value streams that we can collect, and also the treatments, the waste treatment and the disposal stages, which includes building those brine lines or drilling deep wells, preparing those landfills for solid waste. When we add all of these details, that gives us the cost breakdown between stages, and also the calculation of the levelized cost of water and total capital cost. And we can do this in different geographical locations, and also for different desalination technologies, such as the ROs or thermal methods, or any other conceptual ideas, which are such as the membrane distillation, which are still in development stage. So roughly, as I say, the water tap tree, that tree is actually that Parity platform. We just like the IEEE's tree, we have 3 Ps in this acronym. So that water tap 3 will be publicly accessible, which is very important. And this Techno-Economic tool can be used after it's finalized, can be used by anyone who wants to model their water desalination plant or just want to compare the cost estimates from this tool to their upcoming projects or any kind of academic research. So apart from that, the tool will compare process technologies and system pathways constantly on the basis of cost and process efficiency. And this will also include environmental and social impact, which is a very important part, which people usually ask that question. By doing this, are you considering the environmental and social impacts? And this will also cover those issues and will allow the user to understand how the permits can be taken, what kind of discharge methods can be used to eliminate contaminants and pollution. And also this tool will use will help the user to define their own processes. If the user wants to define a different series of process, if they don't want to follow a traditional way of desalination process, they will be they will just create their own processes easily by using this tool. And as I said, this is going to be a transparent and open source tool. And since we are working with 18 different universities in the United States, we are getting feedback from an advisory committee to improve this tool. And we are trying to meet the demand coming from both from the academia and the industry. Okay, so actually that brings me to my concluding remarks. As I mentioned, desalination of water is very important, and it produces like usable water, not only potable water, usable water for municipal, industrial, or agricultural uses. But it was always believed that this is an expensive process, which is true, and it needs to be used strategically since this is expensive water. But on the other hand, there's always a demand for high quality water or potable water in certain areas, both geographically and in certain markets, which are actually willing to pay that price for this water. And also the desalination is a specific interest in certain locations, which the alternatives are also high cost. And so in those cases, it's worth to take that risk of supply and take the risk of that failure or take the risk of that high cost to desalinate the water. But the scenario is not that bad, because the things are getting better every day by developing technologies, and the technological advances are helping us to get a lower cost of desalination every day. And as a result, desalination is becoming increasingly affordable option, and the number of plants are increasing all across the world. So I think that concludes my talk. I think I'm a little bit short on time. We have a lot of time for discussions and questions. And I just want to leave the stage to Kardan right now if we have questions to answer. And I may maybe open the roundtable discussion if anyone has questions or comments on that.
Thank you very much. It was very interesting and educated presentation. I am very educated from there. We have no question right now, but I have one. Do you know the numbers of the all over the world desalination plants or In America, as I saw, there are many, but I don't know, in Turkey, I never saw any desalination plants. Do you know in Europe?
That's a very good question, actually. I don't know the number and how many plants are there, but roughly, if you go back to this chart, this one, so technically you can just estimate. So it's the total installed capacity is about 100 million meter cube per day, and it's like. So you can just think that this is basically between like for single plants. I know examples from biggest plants in the United States. The biggest plants usually have 50 million meter cube per year. So when you look at this number, if you just divide that number by 365, it's usually like 0.2 or 3. So you can multiply this number by at least 5. And roughly you may say between like maybe 100 to 500 plants exist in the world. Roughly. I mean, I don't know the number by heart, but the biggest plants in the United States have roughly 50 million meter cube per year capacity.
Thank you. It's just but
you are right. There's no plant in Turkey yet, which is actually a very good area that the industry, the government, and the universities can pay attention and try to build some projects in that area, which is going to be significantly important, especially considering Turkey's location and water scarcity and in upcoming years, which will be very, very important. This is a very good area of research.
Yeah, that's true. We have no other questions. Then I can take your final remarks, words, and we can finish the session right now.
Yeah, that sounds good. Actually, I tried to speed up a little bit just to be in time, but I was maybe a little fast. I just finished a little earlier. But the final comments are: I mean, if you're interested in this technology, you can reach out to me or some my colleagues at NREL. We can just contact you to the right people to get more information or to get involved in any projects that you may be interested in. And my final comment is: water is important, and renewable technologies are also important. That would be a great match if we can just integrate the renewable energy technologies into water desalination and make this thing green desalination with limited discharge and waste and pollution. This will help us to get a better future and better world for everyone. So thank you.
Maybe postpone the water wars.
Maybe, exactly.
Thank you very much. We have another session in 8 o'clock in Turkey time. Thank you very much for coming here. And this is the end of this session. Thank you. See you in other sessions.